I'll start with a recap of last time, and then we're going to mainly focus on seeing some applications of the sum check protocol today. Before I begin, just let me make totally sure you can all hear me and see my screen. Somebody just unmute and say, yep.
Yeah.
Yes.
Yes, I do.
Cool. Okay, thanks. Yeah, so last time we discussed the interactive proofs model, explained how it is in some sense robust to various tweaks to the definition, whereby there are transformations from some kinds of interactive proofs to others that at least preserve roughly the verifier's time, although not necessarily the prover's time. And I mentioned that kind of all of the interactive proofs we designed in this reading group will naturally have the properties we want. So you don't really have to worry about those transformations after last week. The two of the properties that are good are perfect completeness. So the honest prover always convinces the verifier to accept. And public coins, which basically means all the challenges from verifier to prover are just random field elements. And public coins are nice because any public coin protocol we can render non-interactive with something called the Fiat-Shamir transformation, which we'll probably talk about pretty soon. Okay, so after discussing what are interactive proofs, we introduced the sum check protocol. So just as a quick reminder of what this protocol does. So the verifier is given, quote, query access to an L-variate polynomial G over some field. And let's say, for simplicity, that G has degree at most 2 in each of its L variables. And that will actually be the case for all of the applications we see today. And the verifier's goal is to sum up G's evaluations at all Boolean inputs, that is, at all 0, 1 valued inputs. Okay, so that is a sum over 2 to the L terms. And the verifier, doesn't want to do the hard work of computing that sum itself. So the sum check protocol allows the verifier to kind of force the prover to do the hard work for it. And jumping down a few lines, the verifier's time in the protocol is order L, where L is the number of variables, plus the time to evaluate G at a single point. So, in many cases, evaluating G at a single point will be much easier, much faster than computing this whole sum, which at least naively requires evaluating G at the 2 to the L Boolean points. So the verifier is kind of saving time by using the protocol to force the prover to do the hard work of solving the problem for it. Okay, now there are L rounds, 1 round per variable of the protocol. Each round, the prover sends a univariate polynomial of degree at most 2. Such a polynomial can be specified with just 3 field elements, and hence the proof length is 3 L field elements. The protocol is perfectly complete. So the honest prover always convinces the verifier to accept. And the soundness error is at most, it's not 2, it's 6L over field size. So as long as your field is pretty big, this will be like a tiny, tiny soundness error. Think of L as maybe 30 to 100. So you're talking about something like soundness error is like 600 over field size. Field size could be 2 to the 127, 2 to the 256, whatever. So typically, unless you're working over an insanely small field, this will be really low soundness error. Okay, the prover time is at most order 2 to the L evaluations of G, which is in a sense optimal, because if we don't know anything about G other than that it can be quickly evaluated at a point, there's really no way to solve the problem in the first place any faster than evaluating G at these 2 to the L points that the verifier wants it summed over. Again, if G is structured, as we'll see today, then the prover can typically run faster than this. Okay, so that was sum check protocol. Anyone want to ask any questions before we see some applications of it? Okay, so I am going to start with an application to a problem called counting triangles. I think this is kind of the cleanest application to display kind of the main ideas of how sum check protocol gets applied in practice. Um, people do care about the counting triangles problem. Those people are typically not cryptographers. They're like algorithms people. So I'm bringing up this problem just as kind of a clean demonstration of, the sum check protocol being useful and how to use it. Not because I think you really, really need to know about this problem in particular. Okay. So the input to this problem is something called the adjacency matrix of a graph, and I'll tell you what that is in a moment. So let me call that adjacency matrix A, and let's say it's n by n. Okay, so what a graph is just a collection of vertices and edges between the vertices. Um, our graphs are going to have n vertices, and edges connect two vertices to each other. So a concrete example would be like the Facebook graph, where vertices are Facebook accounts and edges are just like representing friendships between accounts. So vertices are accounts, and AB is an edge in the graph if account A is friends with account B. And we're just deal with undirected graphs. So, like on Facebook, if you're friends with Bob, then Bob is friends with you. There's no way for you to be friends with Bob and the reverse to not be the case. Okay. And with an adjacency matrix of a graph, there's one row per vertex and one column per vertex. I can't draw a brace and columns. And Aij is 1 if I is connected to j by an edge in the graph, and 0 otherwise. So, there is an entry of A for every kind of possible edge that might be in the graph, and that entry is 1 if the edge is actually in the graph and 0 otherwise. Okay, so the number of triangles in the graph is as follows. So you look at all triples of vertices. So let's say ijk and n by n, where this like kind of brace n notation just means the integers 1 up to n. So what I'm saying is we're summing over triples of nodes. So like Facebook accounts, Alice, Bob, and Charlie, triples of vertices. I'll use the term nodes and vertices interchangeably. And they form a triangle if they're all connected to each other. So if I is connected to J, and J is connected to K, and I is connected to K, they form a triangle. So like, this is a triangle, but like this is not a triangle because it's missing this edge. Okay, so yeah, the goal is to just count the number of triangles in the graph. This is a problem, again, that people care about in things like computational biology and social network analysis. And the fastest known algorithm for the problem uses what's called matrix multiplication. So I'll say more about this later, but it runs in matrix multiplication time, which we discussed when we covered Friedwald's algorithm. Currently, the best known algorithm to multiply matrices is something like n to the 2 point, I don't know exactly, 3.6 something. I don't quite remember. But the point is it's super linear in the input size. Right, the input size here is n squared. Okay, so we're going to want the verifier to run faster than the fastest known algorithm. If it didn't, then there'd be no point to using a prover, because the verifier could just ignore the prover and solve the problem on her own. Okay, any questions up to this point? Cool. Okay, so I think the key perspective, it's hardly even like an idea. The key perspective to design this protocol is to view the input A not as an n by n matrix, but rather as a function with a funny domain. So the domain of the function is going to be 0, 1 to the log base 2 of n by 0, 1 to the log base 2 of n. And for each element of that domain, it's going to spit out a field element. Okay. And the point is that, how many bit vectors of length log base 2 of n are there? There are exactly n such vectors, right? Because there are two choices for each of the log base 2 of n coordinates, and 2 to the log base 2 of n is n. Okay, and so we're going to think of like the first log base 2 of n bits of the input to this function as specifying a row, and the second as specifying a column in the matrix. Okay, so what we're doing is reviewing the matrix just as the evaluation table of this function. So pictorially, if we have a 2 by 2 matrix, so say our matrix is 0, 8, 7, 19. We're gonna view this. So using notation, I'm going to view it as a function on 2 bits, because here log base 2 of n is 1. So so this function on 2 bits, 0, 1 by 0, 1. There are 4 possible inputs to it: 0, 0, 0, 1, 1, 0, and 1, 1. Okay, and we think of this as the first bit as indexing the row. Are you in 0 is like this row, 1 is like this row, and the second bit is indexing the column. 0 is this column, 1 is this column. So that is, we're interpreting the matrix as the evaluation table of this function that maps 0, 0 to 0, 0, 1 to 8, 1, 0 to 7, and 1, 1 to 19. And we're interpreting each of these things as field elements. Okay. Any questions about that? Okay, so if you've never, sort of seen, if we hadn't covered multilinear extensions already, you hadn't seen interactive proof, this would be like a very strange way of viewing this matrix as the evaluation table of a function whose domain is, bit vectors. But there's a very specific reason we're doing that. Like once we view A as a function with that domain, it makes sense to refer to its multilinear extension polynomial, which I'll abbreviate MLE for multilinear extension polynomial, and I'll call it A twiddle. Okay, so we saw during our Lagrange interpolation session, right, that I'm just going to restate the theory. So, I gave a statement about kind of fast algorithm for multilinear Lagrange interpolation, and I'll remind you what that algorithm achieves in the context of this multilinear extension A twiddle. So that algorithm was, given as input the entries of A, that is which all evaluations of of this, we're viewing A as a function, right? All evaluations of A when viewed as a function mapping 0, 1 to the log n. All my logs today will be to base 2, so I'll stop writing base 2. Yeah, so when given the algorithm, all evaluations of the function you're extending, the algorithm runs, and the desired evaluation point R. Remember, R will be have 2 log n coordinates, and can take values anywhere in the field. The algorithm will compute. It just evaluates the multilinear extension at the desired point, and it runs in linear time. So in time, in this case, linear in the number of evaluations, which in this case is n squared. Okay. So what's happening is we chose to view this matrix not as a matrix, but as a function whose domain is the Boolean hypercube, so that we could refer to its multilinear extension polynomial. And the verifier in this sum check protocol, when I tell you eventually what polynomial to apply sum check to, but it'll be derived from this multilinear one here, is going to have to, at the end of the protocol, evaluate that polynomial at a random point. And it's going to get that evaluation via exactly this fast algorithm.
Quick question.
Yep.
When we say multilinear, that assumes that there are multiple variables, right? So are the variables just the coordinates or the hypercube coordinates?
Yeah, exactly. So there are two log n variables. So you kind of think of the first log n variables. If they were to take Boolean values, they kind of index a row of the matrix, and the second log n index a column of the matrix, right?
Mm-hmm.
So yeah, it's a twiddle is it's a 2 log base 2 of n variate polynomial, like by definition.
Sorry to jump in because I think this is important.
Yeah.
N squared, the n squared comes from.
Yeah. So if the graph for the graph that we're trying to count triangles in, if it has n vertices, this is the number of vertices in the graph.
Okay.
Then the adjacency matrix has n rows and n columns.
Okay.
And so it has n squared entries. It basically has an entry for like every pair of vertices.
I got it.
Indicating, is this pair of vertices connected to each other in the graph?
Okay, that makes sense.
Yeah.
Because you said something about n squared equaling the size of the field, but that's not. But the finite field can have any. I guess the finite field's only ones and zeros here, even though you put in 8, 7, and 19.
Sorry. So okay. So if I said n squared is the size of the field, I misspoke, and that was confusing. So apologies. N squared is just the number. It's the size of the input. So it's the number of entries in the matrix.
Okay.
And the field size, by the way, we'll need to choose the field for reasons I'll get to in a second. To have size at least, let's say n cubed. Really, what we need is like the max possible number of triangles. That's to avoid some wraparound issues I'll describe later. So the field here, whenever in all of our interactive proofs, the field's always going to have to be reasonably big for a couple of reasons. One is to avoid wraparound issues, which I'll explain more soon. But there's also because of the soundness error, right? The soundness error of sum check is is something over field size, and the field has to be big enough so that it dominates the something. So what's happening here is the domain of A. Before we take its extension polynomial, the domain of A is by definition, we're sort of viewing A as the domain being 0, 1 to the 2 log n. But once we take the multilinear extension polynomial, its domain is no longer 0, 1 to the 2 log n. Its domain is field to the 2 log n. Yeah, A itself, we're viewing this matrix as like the list of all evaluations of some function over the Boolean hypercube. That function has the same number of evaluations, that is the same domain size, as A has entries, just because we're viewing A as the list of all evaluations of that thing. But then when we take the extension polynomial, that thing we can evaluate in the entire field, much bigger domain.
So to confirm, we use a Lagrange interpolation to do to derive the multilinear extension. But so there's basically just 2 variables that are in the Lagrange in this case.
So it's in this little size 4 matrix, there are 2 variables, but in general there'll be 2 log n variables. So let me just do a slightly bigger example then. I think the cleanest next example is actually 4 by 4, which is a little annoying, but anyway. So yeah, I won't write out the whole thing for time reasons, but if your matrix is 4 by 4, so it has 16 entries, the domain then would be 4 bits rather than 2 bits. So
Got it.
yeah, and
Well,
and
hmm.
and we're interpreting like top left as 0, 0, 0 as and bottom right as like all ones, um, something like that. So
Makes sense.
yeah, so this, I'm really glad you're asking questions about this. Like no one did at the session last night, and I think that probably means I lost a lot of them. Because this is a lot to wrap your head around at once, especially the first time you see it. So if this were like a billion node graph, right? Then so if n were 2 to the 30, okay, at that point I think a would be so big you really can't even store it all. But just imagine n were 2 to the 30. Then a twiddle would be like a 60 variant polynomial. So quite a lot of variables. And this is going to get even more confusing as I go, because I'm going to start writing like the first log n variables as like x1, but what I really mean is x1 is consists of log n variables, and x2, the second log n variables as x2, and it's going to look like there's individual variables, but they're not. I mean them to be like kind of vectors of log n variables. So we'll get even more confused as we go. Okay, is that clear enough for now?
Yeah, and the reason that it's 60, it's because you have two options for. I almost had it. It's 60.
Yeah, I'll say it again. So as a picture, if this is A, it has 2 to the 30 rows and 2 to the 30 columns.
Yeah.
And so the number of bits required to like index a row is 30. So with 30 bits, I can tell you exactly which of the 2 to the 30 rows I'm talking about. So each row takes 30 bits to sort of index or specify. And same with each column, which mean and you're thinking of A itself as sort of taking as input like a row and a column,
Got
and
it.
spitting out the corresponding entry of the matrix. Sorry to have used notation. Here it's a matrix and here it's a function. But we're indexing the rows and columns by bits instead of by numbers. So 30 bits specify a row, 30 bits specify a column.
Mm-hmm.
Yeah.
Makes sense.
So
Thank you for.
Oh, go on.
No, thank you for the tangent. That's very helpful.
Yeah. No, I'm really glad you had the questions. Again, I probably just lost everyone last night, and everyone was too polite to ask anything. The same questions come up like every time I cover this, and so I don't know. I think that so far the only way I found forward is to have somebody kind of volunteer to ask exactly these questions. So I'm really glad you did. Thanks a lot.
No worries.
Cool. Okay, so at this point, all we've done is we took the input to the counting triangles problem A, and we viewed it like not as a matrix, but as a function, mapping 2 log n bits to the field in the sort of the natural way. And once we do that, it means we can talk about the multilinear extension polynomial of that function, whose domain is much bigger, because it takes as input like the entire field for each variable instead of just 0, 1. Great. So now I can finally tell you what polynomial we're going to apply the sum check protocol to. Okay, so here's where we get some confusion, some extra confusion. So let G be the following here 3 log n variant polynomial. And this is where I'm going to bring in like x1, x2, x3, but each one I really mean to have log n variables each. So G of x1, x2, x3, and I'll write that out to try to minimize confusion. Log n variables, x1 is log n, same with x2 and same with x3. Okay, it is as follows. I'll come down here, write it down here. Sure, I have enough room. So we're going to multiply kind of 3 copies of a twiddle together. The first one we're going to feed in x1 comma x2. Remember, a twiddle is a 2 log n variate polynomial, right? So if we take x1 and x2 each has log n variables, so x1 x2 together have 2 log n variables, which is exactly the right number to feed into a twiddle, right? We're going to multiply that by x2 x3 and multiply that by x1 x3. Okay, so that's G. And something to note is that G has degree at most 2 in each variable. Right. And what's happening is now I wouldn't really care if it had degree 3 in each variable because it hardly affects the cost of the sum check protocol. The proofs get a little bigger, the soundness error goes up a little bit. But what's happening is even though we have 3 copies of a twiddle, each individual variable only gets fed into 2 of those copies, right? Like x1 gets fed into the first and the third copy. So this factor here, has kind of degree 0, like contributes degree 0 to the variables of x1. Just because the variables of x1 are not fed into this copy here. Right, so for that reason, G actually has degree 2 in each variable. Okay, so all we do is we apply the sum check protocol to G. So I'll state the following as a fact. What does the sum check protocol actually compute? Well, it sums up G's evaluations over the Boolean hypercube. So I guess I'll just write, if x1, x2, x3 in 0, 1 to the 3 log n of G of x1, x2, x3. And the fact is that this is exactly the number of triangles in the graph. And let me remind you what that definition was. By definition, that is, sum over ijk being triples of vertices of aij times ajk times aik. Okay, and what's happened is we define G to extend this thing. Okay, so G is an extension polynomial, but not multilinear because it has degree 2 in each variable. So it's an extension polynomial. Let me say not multilinear. Okay, it was derived from multilinear thing a twiddle, but G itself is not multilinear. It has degree 2 in each variable. So Gn is an extension polynomial of this function here, like I don't know, we map like kind of ijk to aij times ajk times aik, right? So we define G so that this would be the case, right? Because aij, again, I'm there's really no choice for me but to sort of abuse notation here, right? Here I'm viewing A as a matrix and I and J and K as like numbers between 1 and n. But this is the same as aij, where now I and j are Boolean vectors of log n bits times ajk times aik. So I'm just hardly abusing notation, using a both to denote the matrix and the function that we're viewing the matrix as. And if I stick twiddles over everything, because that's an extension polynomial, the multilinear extension now, you don't change the values when ijk are in 0, 1 to the log n, or 3 log n if they're all together. Okay, does that make sense? So we specifically define G so that if you feed into it like the Boolean indices of nodes I, J, and K, it spits out exactly what we want to sum. That is 1 if they form a triangle and 0 if they don't. Does that make sense? So to summarize, summing up all evaluations of G at Boolean inputs will just give us the right answer. And that's exactly what the sum check protocol does, is it sums up all evaluations of some L-variate polynomial for whatever L you want over all Boolean valued inputs. Now, this is why I said the field has to be at least like the maximum number of triangles, because this sum is done in the field, right? G spits out field elements. So if the field is like a prime field of size P, then this sum is computed, modulo, it's all in the field. So modulo the size of the field then. Here, this is, assuming prime field. Really, anyway. So like if you worked over a field of size, n squared, but the number of triangles is n cubed, it will clearly, you'll have a problem because, the answer that computed by sum check will always be a number between 0 and n squared. And the right answer is bigger than n squared. So what happens is, you have what the wraparound issue, where you wind up computing the right answer, not kind of as an integer, but just modulo the field characteristic, modulo the prime. So that's why I said we have to choose the field big enough to not have issues like that. Okay. Great. So that is the protocol. That's the counting triangles protocol. So the only thing left to discuss is just what are the costs for the prover and the verifier. Let me just pause and see if anyone wants to ask a question.
I mean, I have another one. The dot, Are those dots just the way to, are those dot product?
These dots?
Yeah.
That's just multiplication.
Okay.
Right? The definition of counting triangles said sum over all triples of vertices.
Got it.
Yeah, the matrix entries. And yeah, conceptually what's happening is, if your matrix entries are all 0, 1, with 1 indicating like, yes, this edge isn't, I is connected to J, and 0 indicating I is not connected to J. This product is 1 times 1 times 1, or 1, if and only if all 3 edges are there. So if and only if I is connected to J, J is connected to K, and I is connected to K, which is exactly what being a triangle means. So this is, if you want to think about this sort of more intuitively than just, hey, it's multiplication. For any triple IJK, this product here of the 3 entries of A is just like indicating, does IJK form a triangle or not? And then we just sum over all triangles.
Yep. Thank you.
Yeah, thanks for the question. Other questions? Okay. So yeah, let's talk about the costs. So yeah, this is a complete and sound protocol. The soundness error is something like 6 log n over field size. And the proof length is like 6 log n field elements. It's because there are 3 log n rounds, and in each round, the prover sends a degree 2 univariate polynomial. Sorry, I guess 9 log n. 3 log n rounds, 3 field elements per round, because it's degree 2 in each round. I always forget that degree 2 polynomials require 3 field elements to specify, not 2. Okay. The prover, remember, runs in time. Order 2 to the L, where L is the number of variables, times the evaluation time of G. Now, think for a second. It turns out that the evaluation time of G would actually be, in this case, not order n squared, which would be bad, because order 2 to the, remember, L here is 3 log n. So 2 to the L is actually n cubed. So evaluating G at 2 to the L points, like doing each evaluation completely independently of each other and very naively, is actually going to be n to the 5th time, which is like really, really slow. I mean, it's still polynomial, but it's really bad. It turns out with a little bit of cleverness, you can actually make P run in just n cubed time. So that's, I've kind of been indicating whenever I talked about prover time that, like if you know nothing at all about G, then in the worst case, like just to solve the problem, you have to evaluate G at 2 to the L points just because the sum's over 2 to the L terms. And but that often you can do better because G is structured. And so this is an example where, so there are n cubed terms, and but it turns out that you kind of don't have to do all the evaluations of G independently of each other. There's some structure to G. In particular, it's a product of 3, multilinear polynomials, each of which can be evaluated in n squared time. So anyway, so just, I guess, believe me, since I don't want to go into great detail, that the prover can run in n cubed time, which is actually, the number of terms in the sum. So it's, yeah, I'll just stop babbling there. And n cubed time is the prover time for this protocol. And then the verifier time, so it has to, process each of the messages from the prover, but there's only logarithmically many of them. And then it has to evaluate G at one point. So eval time G. So what is the evaluation time of G? Well, if you want to evaluate G at R1, R2, R3, where each of these is in, is a log n dimensional, vector of field elements. Well, that is just a twiddle evaluated at R1, R2 times a twiddle evaluated at R2, R3 times a twiddle evaluated at R1, R3. Okay, and remember, there is, using fast multilinear Lagrange interpolation, there's an order n squared time algorithm, and n squared is the size of the input here. So that is, quote, linear time, linear in the size of the input. There's an n squared time algorithm to evaluate each of those 3 things. Okay, so the verifier time is order n squared, which is the time required, like, just to read the input in the first place. So the verifier time up to a constant factor is the best you can hope for. Okay, questions? Cool. Let me see if I want to say anything else. Yeah, so I'll mention this prover time n cubed. This matches like the runtime, not of the best known algorithm for counting triangles, but the straightforward algorithm for counting triangles. Kind of the naive one that just iterates over every triangle and every possible triangle and sees, is it a triangle or not? So, we can kind of hope for the prover to be even faster, than n cubed time, but at least the prover here is really no worse than running the straightforward algorithm that people actually would use on small graphs anyway, because the smarter algorithms don't get better than the straightforward algorithm until the graphs are pretty big. So, it's something like n cubed time might sound like not great for the prover, but it's as good as kind of this straightforward algorithm. Yeah. So if you're not at least a little bit clever in the design of your algorithm, even for getting proving, you can actually do better than n cubed anyway. Okay. Great. So that is a cool interactive proof. Hopefully, the main idea I want to convey here is this funny way of viewing inputs that are, naturally thought of as vectors or matrices, not as vectors and matrices, but instead as functions whose domain is the Boolean hypercube. Because once we take that view, which kind of a priori, if you've never seen this stuff before, is like a very strange way to view a vector or a matrix, we can start talking about multilinear extensions of the input. And that's a very powerful thing, because like all we do is apply sum check here to kind of a product of kind of 3 copies of that multilinear extension. And like we're done. We've given this interactive proof where the proof length is logarithmic and the verifier runs in optimal time, like linear time in the input size. So it's a very powerful, strange way of viewing vectors and matrices and things as functions over the domain 0, 1 to the log n, where n is the input size, which lets you take these multilinear extensions. Okay. Feel free to jump in with a question. If no one has one, I will continue onward. And I think it makes sense to just keep seeing applications of SumCheck, because you kind of get more and more comfortable with the hammer, like the more you see it used. So the next thing I want to talk about is matrix multiplication. And this is a nice one to talk about, actually, because I think this is going to get used a lot soon. Basically because matrix multiplication is like a key operation done in machine learning. And there's a lot of interest in ZKML these days, which is kind of like snarks to prove you've done machine learning correctly. And if you want this to scale, you're going to need what I call a super efficient protocol, meaning the prover. This is super efficient is a term I just made up, but it means the prover like runs the best known algorithm for the problem. And then does a low order amount of extra work to prove the answer is correct. Right. So it might spend, 20 minutes solving the problem, but only does a second of work to prove that the answer is correct once it knows the answer. So while counting triangles is not a problem anyone cares about, really, not in Snarkland anyway, matrix multiplication is. But I'm also covering this because I want to kind of demonstrate the power of interaction in I think a very clear way. So we're going to give an interactive proof for matrix multiplication. I am then going to use it to give a better interactive proof for counting triangles. So we just gave one where the prover time was n cubed, and I'm going to explain how to get a super efficient one where the prover time is better than n cubed. And in so doing, we'll see, why that protocol is better than the non-interactive matrix multiplication protocol due to Frivold's that we covered several weeks ago. And that's probably all I'm going to get through today, which I think is fine. I think seeing these three applications of SumCheck kind of direct, the counting triangles protocol we just saw, and then this matrix multiplication protocol, and then the better counting triangles protocol. I think that's a pretty good session to just kind of get comfortable with applying the SumCheck protocol. Okay, so let's talk about matrix multiplication. So here, remember the input is two matrices A and B. Let's say they're n by n matrices with entries from a field. And the goal is to compute their product, A times B. And let's say that the prover, so remember in Frivold's algorithm, the prover sent the claimed answer, C, to the verifier. And then the verifier sort of through a fingerprinting technique in linear time kind of checked probabilistically, does C actually equal the true answer A times B? Okay, so this interactive proof is going to give a different way of checking that C equals A times B. And it might seem a little silly to give a different way of checking does C equals A times B, because Frivold's already gave away, and Frivold's way runs in linear time, so how can you possibly improve it? But we'll see that you can improve it, because in a lot of settings, the verifier doesn't actually care about the claimed answer matrix. It's sort of, the claimed answer matrix is just a means to an end. It's like an intermediate value arising in a computation, and the verifier only cares about the final value of the computation, not the intermediate one. And we'll see with interaction, the prover will not have to send the product matrix to the verifier, whereas without interaction, the prover would have to send the claimed product matrix to the verifier. So that will make sense when I cover the super efficient interactive proof for counting triangles, this whole thing about the prover not sending product matrices to the verifier. Okay, so this is how the verifier is going to check whether C, the claimed answer, equals the true answer A times B. Okay, so the verifier will pick R1 comma R2 at random from field to the log n by field to the log n. Okay, and in order n squared time using fast multilinear Lagrange interpolation, V will evaluate the multilinear extension of the claimed answer at R1 comma R2. Okay. Now I want to be clear about something because a lot of people get confused by this, understandably so. When this might look like a single entry of C, it is not. So this, if as long as R1, R2 are like not in let's say as long as they're not Boolean. So let's say none of their entries are Boolean. So let's say they're in the field set minus like the I want to say I just write it. As long as no entry of R1, R2 is Boolean, okay, then like every entry of the matrix C contributes to C twiddle at R1, R2, right? This is just, you can see this from multilinear Lagrange interpolation. C twiddle of R1, R2 equals sum over all, ij in the Boolean hypercube of Cij, if you view it as a function over the Boolean hypercube, times the Lagrange basis polynomial for ij evaluated at R1, R2. And what my point is, if no entry of R1 or R2 is in 0, 1, then this will be non-zero for every ij in 0, 1. Okay, and if that's the case, then every single entry of C is sort of contributing to the sum, is getting multiplied by something non-zero. Okay, so while C twiddle of R1, R2, like kind of if you didn't have the twiddle there and R1, R2 was just like Boolean, they would just spit out like a single entry of C. If R1, R2 is like, if they're not Boolean, then every single entry of the matrix C winds up like contributing to this value that the verifier computes. So it's just one field element. So it's like, they can't possibly have more information than like a single field element, but every one of the n squared field elements in C contributes to that single field element. Okay, and that's like kind of the key. Like to remember, Schwartz-Zippel says that any two distinct low degree polynomials disagree at almost all inputs, but that's referring to random inputs from the whole field, right? Like two matrices can disagree on just a single entry, in which case, if you just look at like a random entry, even though they're not the same matrix, they'll almost certainly like look the same at that entry. That's not what's happening here. If any two matrices disagree in even a single entry, their multilinear extensions will disagree almost everywhere. But the key is like everywhere there is over the entire field. So this is not like a randomly chosen entry of C. It's a randomly chosen evaluation of C twiddle. So apologies if I keep kind of saying the same thing over and over again, but many people have gotten confused by this previously. Okay. Now, the reason the verifier evaluated C twiddle of R1, R2 is because it's basically just doing like a fingerprinting test here. So, because any two distinct low degree polynomials disagree almost everywhere, kind of if C does not equal A times B, then their multilinear extensions will disagree at this random point R1, R2 with high probability. Okay, which means that if the verifier goes and manages to compute A times B twiddle at the same random point, then like if they match, the verifier, it's safe for the verifier to believe that A times B and C are in fact the same matrix. Right? Because again, if they were not the same matrix, then the prover would have to get really lucky over the choice of R1, R2 for this match to occur. Okay, so the rest of the protocol is really just an interactive proof to compute the multilinear extension of the product matrix at R1, R2. Okay, so that's what the rest of the protocol is devoted to. Does anyone want to ask a question? Okay, so I'm going to give an explicit expression for this, and that expression will render this value amenable to computation via the sum check protocol. Okay, so here's the fact. The fact is that A times B twiddle, so the product matrix multilinear extension of that, I'm just going to give an explicit expression for it, similar to how Lagrange interpolation gave an explicit expression for the multilinear extension of any function in terms of its evaluations over the Boolean hypercube. So here's the explicit expression for this polynomial. So it's the sum over all k in 0, 1 to the log n of a twiddle x1 comma k times b twiddle of k comma x2. Okay. Now, if I ever give you, two multilinear polynomials and I claim they're the same polynomial, you can confirm that claim, and that's what I'm doing here. I'm going to call a claim instead of a fact. You can confirm that claim check two things. So one is we want to check the right-hand side, which is left side. Thus the left side is and the right-hand side here. And then that they agree all input. The number of them is 2 log n. Okay, if you check these two, it'd be the multilinear extension of the product matrix A times B. Okay, the right-hand side is multilinear because A twiddle is multilinear and X1 is fed into the first copy of A twiddle, but not the second. Or sorry, but A twiddle is multilinear and X1 is fed into A twiddle, but not B twiddle. And similarly, X2 is fed into B twiddle, but not A twiddle, and B twiddle is multilinear. Okay, so this is just a sum over, n terms, one for each value of k. And for each term, you fix k and you get, something. And that something is multilinear. So you're just summing up a bunch of multilinear things, and that's multilinear. Okay. So that's how to confirm that both the left-hand side and right-hand side are multilinear polynomials. And then checking that they agree on all inputs in 0, 1 to the 2 log n. Well, that's just the definition of matrix products, because A times B, like its ijth entry, is the sum over all entries k of aik times bkj. And that's all that's happening here as well. If you restrict x1 and x2 to be Boolean, and k is obviously just summed over Boolean values, because A twiddle extends A and B twiddle extends B, you wind up just if you fix x1 to like I and x2 to j, this is exactly the sum you get out, sum over k of aik times bkj. So the left-hand side being the multilinear extension of the product matrix A times B, the right-hand side, well, it also kind of extends the product matrix A times B. So we've done both. They're the same polynomial. Okay, any questions about this claim? Okay, so as a result, we know that what the verifier wants to know is, A times B twiddle of R1, R2. And we just showed that that equals the sum over k in 0, 1 to the log n of A twiddle R1 comma k times b twiddle k comma r2. Okay, so if we let g be the log n variate polynomial of degree 2 in each variable, given by g of k equals a twiddle r1 comma k times b twiddle k comma r2, then applying sum check to g computes sum over Boolean inputs k and 0, 1 to the log n, g of k, which I just said is exactly a twiddle of r1 comma r2 as desired. Sorry, not a twiddle, a times b twiddle. Sorry. Yeah, so that's the sum check protocol. Is you apply sum check. That's the end of the matrix multiplication protocol. Is you apply sum check to g. Okay, so just apply sum check to this polynomial g. That's it. Okay, so it turns out that so let's talk about efficiency. So proof length. So there are log n rounds, and there are 3 field elements sent per round because the polynomial has degree 2 in each variable. And the verifier time is the time required to process those messages, which is order log n field operations, plus the time to evaluate g at a single point. Now evaluating g at a single point, say r3, is a twiddle r1 comma r3 times b twiddle r3 comma r2. Okay, so evaluating g at a single point entails evaluating a twiddle and b twiddle each at a point. And remember, each of those can be done in order n squared time via fast multilinear Lagrange interpolation. Okay, so the verifier time is linear, which matches Friedwald's algorithm. And finally, the prover time. So I'm not going to go into the details here, but something cool is once the prover knows the true answer a times b, the prover's additional time is just n squared. So this would qualify as super efficient in that the prover just computes the right answer and then does n squared additional work to prove that the answer is correct. Now, that might not sound super interesting because Friedwald's algorithm had literally no extra work for the prover. The prover just sent the right answer, and that's it. But we're about to see some benefits of the interactive proof over Friedwald's algorithm. And those benefits become apparent in a super efficient IP for counting triangles.
Excuse me, I have a question
Yes.
regarding this algorithm.
Mhm.
I'm not sure I understood clearly. You said that it was interactive, but
Yeah.
I see only one interaction and not log n interaction.
It's because the sum check protocol is getting applied to this log n variate polynomial g, and there's one round of sum check per variable of the polynomial that is getting applied to.
Oh, G is not constructed by the verifier?
So g, the verifier winds up only evaluating g at a random point, and otherwise it doesn't actually know anything about g, really. So
Okay.
remember, yeah, you can apply, this is a little subtle. You can apply the sum check protocol to any polynomial. The verifier doesn't even know what have to know what the polynomial is until the very, very end when it has to evaluate that polynomial at a random point. And this polynomial can be evaluated at a random point by evaluating a twiddle and b twiddle at a random point each. And we know how to do those evaluations in linear time. So, in a sense, the verifier doesn't even know what g is. All it's able to do is evaluate that it knows just enough about the polynomial to evaluate it at a random point quickly, and that's it. It couldn't tell you what its coefficients are or anything like that.
Okay, yeah. Oh, okay, I think I'm because G is the interpolation of the matrix C.
No. So, yeah. So what happened in the whole protocol here? Let me just write out the whole protocol. All
It's just
right.
because I've seen two G functions.
Two G functions. There was a G function in our counting triangles protocol
Ah,
before.
okay, yeah, okay. Okay, sorry.
Yeah, no
Okay, I
problem.
see my mistake.
I shouldn't have reused G. Yeah, I try to use G to denote the polynomial sum check gets applied to, but then if we see different applications of sum check, you forget which, what G is since there was a different G before. I'll just write it out real quick. It's a pretty quick protocol to write out in full. So the prover sends to the verifier the claimed answer, C. Sends that. Okay, so the verifier on its own computes in linear time C twiddle of R1, R2 for some randomly chosen points R1, R2. It does have to send R1, R2 to the prover. Okay, and then they apply sum check, so I guess this is a log n round protocol. They apply sum check to the polynomial GK, which is defined as a twiddle of R1 comma K times B twiddle of K comma R2. And that, yeah, and then the verifier, like confirms the result, which is sum over x in 0, 1 to the log n of g of x equals c twiddle of R1 comma R2, which had already computed up here. That's the whole protocol.
Okay. It's clear to me. Okay, thank you.
Yeah, thanks for asking, and sorry for the confusion. Yeah,
No, my mistake.
great. Other questions? Cool. Okay. Yeah, like something to note here is that what we really gave was an interactive proof for computing, for evaluating the multilinear extension of the product matrix at a random point. Okay, like that's what this sum check, like right here, like this sort of subroutine. This is all this is just an interactive proof for computing something a little funny, the product matrix multilinear extension at some point of the verifier's choosing. Okay, so like the only reason for the prover to send a claimed answer and was really for the verifier to be able to evaluate the claimed answer multilinear extension at a random point. Like if there was some other way to get the verifier the claimed answer evaluated, its multilinear extension evaluated at a random point, we wouldn't need prover to send the claimed answer, right? All the verifier really needs is that MLE evaluation. Like the only thing that the verifier basically, it got to forget about the claimed answer as soon as it computed just this one field element. Okay, so this is going to become a little clearer in this counting triangles protocol we're about to see. Right, but the verifier didn't even need to know the whole claimed answer to like check its correctness. It just needed, I think of this as like a fingerprint of it. I just needed that fingerprint. Okay. So going back to counting triangles, I'm going to give a second interactive proof for it, and it's going to be much better for the prover. So for the verifier, it's going to be like almost literally the same in terms of complexity, but the prover will be better. Okay. So remember, given the adjacency matrix A of the graph, so that's the input. The goal is to compute sum over all ijk of triples and nodes of aij times ajk times aik. And fact or claim is that this is the same as summing just over ij, so pairs of nodes now, of the squared adjacency matrix at ij times the original adjacency matrix at ij. Okay, so there's a conceptual way to see this, which is that a squared ij conceptually, it turns out to equal the number of kind of length one paths between I and j. So that is the number of k, such that I is connected to, let me put it this way, k is connected to I and j. I guess the picture should be, well, I'll write it this way. So I is connected to k, that's connected to j. Now these are undirected edges, so I'm going to put arrows here, but yeah, you can ignore the arrows. Okay, and you can just see this from the definition of matrix multiplication, right? Like a squared ij is sum over k of aik times akj, which is counting exactly these structures in the graph. I is connected to k is connected to j. And so yeah, that's how to interpret a squared ij. And then if a squared ij is some number, and moreover I is connected to j, okay, then we have a triangle, because then the picture is like a squared ij counts structures of this form, but then if moreover I is connected to j, we have a triangle because they're all connected to each other. Remember, these are like undirected edges, so they go in both directions, so they're all connected to each other. Okay. Yeah, does anyone want to ask a question about that? Was that clear enough? Why the number of triangles in the graph can also be expressed as the sum over pairs of nodes of a squared evaluated at that pair times a evaluated at that pair? Cool. Okay, and so the benefit of re-expressing the sum this way, as far as sum check goes anyway, is now rather than the sum being over 3 log n variables, it's over 2 log n variables. That is, rather than the sum being over n cubed terms, which is what caused the original, the prover in our original interactive proof for triangles to be n cubed time, the sum is only over n squared terms, not n cubed. Okay, which means we can hope for the sum check prover, solving this sum to run in n squared time instead of n cubed time. And indeed, we'll achieve that. Okay, so the first thing you do is apply sum check to the following polynomial g, which is going to have 2 log n variables and degree 2 in each variable. So we've got 2 log n variables, degree 2 in each variable. So that polynomial is g of x1 comma x2, each of which is log n variables. Equals, okay, so the multilinear extension of a squared evaluated at x1, x2 times the multilinear extension of a evaluated at x1, x2. Okay, so you apply sum check to that and you wind up computing, the sum over all x1, x2 and 0, 1 to the log n of a squared, twiddle x1, x2 times a twiddle x1, x2. And, by the same reasoning as before, with everything being extensions and us only summing over Boolean things, that exactly equals this sum here. Okay, so applying sum check to this g will give us the number of triangles in the graph. Okay. And the cool thing is it's known, I'm not going into details, like once the prover knows what a squared is, it can actually run the sum check protocol in n squared time. So it actually takes more time, according to the best known algorithm, to compute a squared than for the prover to apply the sum check protocol to this polynomial to prove correctness of the number of triangles in the graph. So where things get annoying is at the end of this invocation of the sum check protocol, V needs to evaluate G at a random point, G of R1, R2, and that equals a squared twiddle at R1, R2 times a twiddle at R1, R2. Okay, and while the verifier can evaluate a twiddle in linear time, n squared time, because it knows the input is A, it sees A. So by fast multilinear Lagrange interpolation, it can evaluate the multilinear extension in n squared time. The verifier does not know A squared. So it can't on its own evaluate the multilinear extension of A squared at a random point, unless it did the hard work of computing A squared, which at which point it's basically solved the counting triangles problem, because once it knows A squared, it can very quickly solve the counting triangles problem. So the problem here now is V does not know A squared, and hence it can't evaluate A squared twiddle at a random point. Okay, but fortunately, we've just given a interactive proof for exactly this task, right? So we just saw an interactive proof to compute A times B product twiddle R1, R2, for input matrices A, B. And so just set B equal to A. So let me just set B equal to A. And yeah, so we just literally saw an interactive proof to compute A squared twiddle at R1, R2, which is exactly what the verifier needs to do at the very end of this application of sum check for counting triangles. So that's, rather than the verifier evaluate A squared twiddle at R1, R2 on its own, it uses the interactive proof we just saw. So it applies sum check again, second time, to I'll call it maybe H of K now, which it's A twiddle R1 comma K times A twiddle K comma R2. And that will yield, that application of sum check will give exactly what the verifier needs, namely the relevant evaluation of A squared twiddle. Okay, so that's it. So the verification costs of this protocol are almost identical to the original interactive proof for counting triangles we saw. So that protocol applied sum check once to a 3 log n varied polynomial of degree 2 in each variable. So that was something like 6 log n field elements spread over 3 log n rounds, in the proof. Here we applied sum check once to a 2 log n varied polynomial of degree 2 in each variable, and then again to a log n varied polynomial of degree 2 in each variable. And you sort of wind up in the end with the same number of rounds and the same proof length. It's just here the rounds are conceptually split over 2 different applications of sum check, whereas in the original one there was just a single application of sum check to a bigger sum. And again, the really cool thing though is the savings in prover time. So again, the prover, once it knows the squared adjacency matrix, which it has to compute just by virtue of running the fastest known algorithm for the problem, actually, the algorithm computes this matrix. The prover just does order n squared extra field operations to prove correct, to compute the proof. To answer, to compute all of the messages across all, both invocations of subcheck. So that's what I mean by super efficient. This extra work is a low order additive term compared to just running the fastest known algorithm for the problem. And the final comparison I want to make is to Frivold's algorithm. So with Frivold's, the prover would have just sent A squared to the verifier. The verifier would have checked probabilistically that indeed this matrix the prover sent is equal to A times A. And that is exactly what we've avoided here, right? Because the verifier didn't care about A squared, it just wanted the number of triangles in the graph. So with interaction, we were able for the prover to only send in total like 6 log n field elements in the interactive protocol, which is vastly smaller than the n squared field elements using Frivold's, because Frivold's would have had to send the product matrix. And my last comment, and then we can call it a day. Of course, if anyone has questions, I'm happy to stick around till 1. Is that in Snarkland, what people would do typically, rather than sending this giant intermediate value, this to the verifier that the verifier didn't actually really care about, the prover would have cryptographically commits to A, thereby avoiding sending A squared, thereby avoiding sending A squared to the verifier. So you with cryptography, you can use sort of older techniques like Friedwald's and regain succinctness. So and then V and P can kind of apply. It can apply Friedwald's, to the committed matrix, without the prover ever revealing what's inside the commitment. Like that's the sort of thing that snarks do a lot. Prover commits to something succinctly, and the verifier kind of is able to do checks on the object inside the commitment without ever actually opening up the commitment and looking at the whole object. So you can get something like, similar to what this protocol achieved today with, very small proofs, much smaller than sending the whole matrix using cryptography. But you completely lose the super efficiency property, or at least it's certainly much more expensive for the prover than what I just described today. The reason being that cryptographically committing to things is expensive for the prover. Like it's a lot of time. If this is a really big matrix, computing a commitment to it will take a lot of time. Cryptographic work tends to be slow. Field operations are fast. Cryptographic operation, like to commit to a matrix of size 1 billion, might be something like 3 to 4 orders of magnitude slower than just doing 1 billion field operations or something like that. So this is really what I think the power of the sumcheck protocol is it lets the prover kind of establish that it correctly materialize in its own head key intermediate values like this squared matrix A squared without even while doing essentially a low order amount of extra work. In fact, in particular, not even cryptographically committing to those values. So the very, very first thing that most snarks do is they just have the prover commit to literally every intermediate value that arose over the entire course of the computation. And there are contexts such as what we just saw today where that's not necessary. You don't need to compute such a cryptographic commitment, which is often the bottleneck in the snark. So that's one reason I like to focus so much on sumcheck and why I'm kind of bullish on its utility moving forward. Okay, I think that's everything I wanted to say today. So hopefully this clarified how to use sumcheck and why, even though the problem it solves looks a little artificial, like summing up evaluations of a multivariate polynomial over the hypercube, in fact, it captures a lot of natural things. Like just with a little cleverness, a lot of natural problems can be phrased in exactly that way. Yeah, so I'll stop here. Next week, I have to decide. We might move on to the GKR protocol, or I might start talking about fiat Shamir. I don't know. So GKR protocol, which is another interactive proof based on sumcheck, but just much more complicated one. Or I might move on to fiat Shamir. I might want to, because GKR protocol is technically quite challenging. I don't want to scare people away by covering it, earlier than I need to. So I might move on to fiat Shamir, which is both more widely applicable and kind of less technically sophisticated a topic to discuss. Yeah, anyway, so that's so this I think is chapter 5 of the book, whereas GKR protocol is the end of chapter 4. So I might just skip GKR and come back to it later, maybe. Anyway, okay, so that's everything I had to say today. Let me know if you have questions, but otherwise, thanks so much for coming this week and staying for almost 90 minutes, and have a great weekend. I'll see you next week.
Thank you.
Thank you.
Thank you.
See you next week.
Thank you.
Bye.